Now we're starting to think about electric current, electric charges moving. And one of the basic points that we start with is the so-called continuity of current or conservation of current. So just imagine some wire, and there's current moving through it. I is our usual symbol for wire. And say at this point there's some particular value of current. At this point there's some particular value of current. Current just means the rate at which charge flows past any particular point. Like some number of coulombs per second here, some number of coulombs per second here. Let's imagine, this turns out to be not true, but let's imagine that the current here is larger and the current here is smaller, I1 bigger than I2. So what happens? There's more charge coming into this region than there is going out. Right? The flow of charge here is faster, higher than the flow of charge here, so more charge is coming in than going out. Charge piles up here, and that's what I've drawn down here. That ordinarily we always imagine current as the flow of positive charge, even though in most everyday situations current is made up of negatively charged electrons that are moving. Anyway, because I1 is bigger and I2 is smaller, charge piles up here. Well, what happens then? Any more charge that's coming into this region sees more than usual amounts of positive charge piled up ahead here, and that applies a repulsive force, a stronger than usual repulsive force, because there's more charge piled up here than usual, and so there's a backward force on the charge that's flowing in, but charge still flows in. The electric field that's actually responsible for making charge, pushing charge around in the first place, still applies a force in the correct direction to make current flow. So there's a net force, the combination of these two forces. The stronger than usual backward force, because there's more charge piled up here than there should be, and then the forward pushing force caused by the electric field. So there's a small net force that's backwards. So a net force backwards on things that are moving this way, of course, slows down those charged particles that are moving this way. Anytime the net force points opposite to the direction of motion, the thing has to slow down. So in that case, that makes I1 decrease, a negative change in I1. So I1 slows down. As a result, the rate at which charge piles up in here decreases. So a decreasing rate at which the charge piles up in there. And then let's look at what happens here at the other side. As charge flows out, it sees greater than usual amount of positive charge behind it. So of course this is repelling all the positive charges that are flowing out through here and producing I2, current 2. So more than usual repulsive force pushing from behind means a stronger than usual forward force. But there's always a backward force as well. The backward force comes partly from positive charge that's in front here and repelling the positive charge that's trying to move to the right, and also comes from the fact that there are lots of atoms and ions here presenting obstacles to the path of the flowing particles. But anyway, because there's more charge behind than usual. There's a stronger push from behind than usual. So then there's a net positive force on current 2. Current 2 is moving this way, and there's a net force pushing it forward. So that means it's going to speed up. So the rate at which charge passes by this point is going to be increasing. I2 is increasing. So what's happened here? I1 is decreasing, I2 is increasing, which means the rate at which charge is coming in here is decreasing. The rate at which charge is flowing out is increasing. So charge is now getting emptied out a little faster, while charge coming in is piling up more slowly. And eventually, the increased flow in, or the decreasing flow in, the slower flow in, and the faster flow out empties out the extra charge here. And then once there's no extra charge, there's no imbalance between the forward and backward forces. Like, imagine what's happening here to I1 as it comes in. At first, it feels this strong backwards push from all of the extra charge that's ahead of it, and then the forward push caused by the electric field is there, but not strong enough, so there's a net force backwards. But charge is emptying out of that region, so the forward pushing force from the electric field stays just as strong as it is always. But with charge emptying out of this region, the backwards push, the repulsive force from all of that extra charge is decreasing because the amount of extra charge in here is decreasing. So there's still a net force backwards, but it's getting smaller. And then eventually, as more charge flows out, the backwards push from this extra charge gets smaller and smaller until finally it's decreased so that it's now the same size as the forward force caused by the electric field. And backward force and forward force are the same strength. They cancel each other out, so the net force is 0. So at that point, now all the charged particles now have a constant velocity. No net force means no acceleration, so constant velocity. In other words, I1 stops decreasing, and something similar will happen to I2. As I2 flows this way, it feels more charge behind than usual, so there's a stronger repulsion pushing I2 forward. The backwards force that it feels from all of the atoms and ions that are blocking the path is still there. It's the same as always. But the forward push from the extra charge is extra strong, so there's a net forward force. Net forward force, of course, increases the speed of all the particles that are moving this way, so that means this region gets emptied out a little faster, decreasing the amount of extra charge. So then the force, the repulsive pushing forward force caused by that extra charge decreases, and eventually decreases until it's equally strong, until it's just as strong as the backward stuff. And again, at that point, I2 has stopped increasing when the extra charge has emptied out. So what do we have here? Long story short, if I1 is bigger than I2, charge piles up, and as a result of that pile up of charge, I1 decreases and I2 increases, and eventually they balance out again. So the moral of the story is, if there's a different amount of current at two places, that means charge could pile up to an unusual amount, or the opposite could happen, charge could empty out here. But if those things happen, that situation doesn't stay that way. The imbalance of charges will cause extra force that will change the values of these currents and bring them back into equilibrium. If there is ever any different current at different points, it can't stay that way. In other words, this produces a pileup of charge which causes new forces which change those currents, decreasing the current that was bigger, increasing the current that was smaller until they balance again. So the result is, over the long term, those 2 points can't have different values for current. Or to put it more generally, the current is the same anywhere inside an electric circuit or in any path through which current is flowing. The same current at every point, right? The same number of coulombs per second passing by this point as you have passing by this point. Same amount. And that's called conservation of current. Let me get my eraser. Okay, now imagine here's a little piece of current carrying wire. And let's say that there's different values of electric potential at different points here. Higher potential here, lower potential here, and these two might be connected to the positive and negative poles of a battery to give them different potentials. Well, we know from this rule, anytime there is a potential difference, there must be electric field. And as you've seen in class, we also know that the electric field always points toward decreasing potential. Electric field always points from higher towards lower potential. Here's higher, here's lower potential, so the electric field inside the wire points that way. We also know that the direction of electric field is the direction of the force a positive charge would feel. So the positive charges that we imagine to be making up our current will feel a force this way, because that's what the direction of electric field says. So the force, the force from the electric field on the positively charged particles that make up the current. So the charged particles that were just sitting still before the current started now have a push to the right, so they gain velocity to the right, but you know that they don't gain velocity forever, because when you throw the switch and turn on current, very quickly you get to a constant current and it stays constant. Well, constant current would mean that the velocities of these charged particles are constant, which means that the net force must be zero. So there must be some other force in the backwards direction that eventually cancels out this forward pushing force from the electric field. And we can think of that as a drag force, just like the drag forces that we thought about back in 2201. Back in 2201, we thought of drag force as happening anytime some mass moves through a fluid, either a liquid or a gas. As it moves through the fluid, it collides with molecules of the gas or the liquid, and each collision is a tiny little backwards push. And the grand total of all those little backwards pushes might turn out to be a significant amount of backwards push. Similar thing happens here. As the particles move through this wire, the wire, of course, is not empty. There are lots of atoms and ions that get in the way of the moving particles. The ions, especially being electrically charged, will apply forces to the charged particles that constitute the current, apply forces to them and change their paths. And overall, that results in a backwards force. One thing we learned about drag forces is that they depend on the speed of the mass that's feeling the drag force. Higher speed means more drag force. So, as at the instant you turn on the electric field, that is, the instant you turn on the potential difference that creates the electric field, at that point the particles that will form the current are just sitting around at zero velocity, and at zero velocity there's no drag force, because the way a drag force operates, the magnitude of the drag force is directly proportional to some power of the velocity. Maybe velocity to the first power, maybe velocity squared, but in either case, as velocity increases, strength of the drag force increases. And when there's no velocity, there's no drag force. In order to collide with all of the obstacles in their path, the charged particles have to be moving. Otherwise they don't collide, and then they don't feel a drag force. So, right at the start, when you first turn on the electric field, all of those particles feel nothing but the forward pushing force that's caused by the electric field. And since at this instant they're starting at rest, they don't have any velocity yet, so they don't feel any drag force. That's the only force on them. So that's the net force. Then they speed up a little bit. They speed up just a little bit. So now they've got a little bit of velocity, so they have a little bit of drag force. The electric field is the same as it always was, so the force caused by the electric field is the same as it always was. But now there's a drag force which points in the opposite direction and thereby cancels out a little bit of the forward force. So now the net force is still pushing forward, but it's smaller than before. In other words, at both this time and this time, there's forward net force, so there's forward acceleration. So at both of these times, the charged particles are gaining forward velocity. It's just that now the net force is smaller, so the acceleration is smaller, so the rate at which forward velocity is gained is smaller. But it's still gaining forward velocity. It's still being pushed by a net force in the direction of motion. And we know that any time a mass is pushed in the direction in which it's already moving, it must speed up. So if it speeds up, the drag force gets a little bit stronger. So now at some time after this, the push caused by the electric field is the same as it always has been, but those particles have been speeding up. So the drag force has gotten stronger, so now it's canceling out even more of the forward force than before. So there's still a net force in the forward direction, but it's much smaller than before. So here at time 1, there's a lot of forward net force, so there's a lot of forward acceleration. Now there's less forward net force, so there's less forward acceleration. And now the net force has gotten even smaller, so there's even less forward acceleration. There's still some acceleration, so the charged particles are still gaining velocity in the forward direction. So they're still speeding up, and as long as they're speeding up, the drag force is increasing. So the drag force keeps on increasing until it gets just as strong as the pushing force from the electric field. So at some later time after this, the force from the electric field is just as strong as it always was, but now the drag force is just as strong as that. So at that point, the net force is 0, so the acceleration is now 0, and that means 0 acceleration, then the speeding up stops. 0 acceleration means constant velocity. Once this situation has been achieved, those charged particles will now move forward at a plain, steady forward velocity, no more acceleration. That's, from this point on, the current is constant. This all happens very, very, very quickly after you've turned on the switch of the circuit. Happens very quickly, but it's a process that does take some amount of time. It's not instant. It takes some millionths of a second or something like that to happen. Now, what's actually happening when those charged particles move through the wire, electric field pointing from high potential to low potential, and the net force that's pushing them forward is the force that comes from the electric field. And that's a force in that direction, pushing positively charged particles from higher towards lower potential. But as I've said before, there are obstacles in the path of the particles, so their path is not just a straight line. The path might look something crazy like that. But the way it works out is that if you look at just take the distance between here and here and divide by the amount of time it took the particle to get from here to here, then you've got an average velocity over this time interval. And then do the same between here and here. See how much time it took the particle to get from here to here, and divide the distance by the amount of time it took to get from here to here, and you've got another average velocity. Well, it turns out that those average velocities are the same, which is just what you would expect, since we've already seen that current is the same at every point in the path of or current is the same at every point in the current's path. This constant average velocity that you get once the net force on the charged particles is gone to zero, we call a drift velocity. Drift because the charged particles aren't just moving in a straight line all the time, they're kind of drifting around, but overall moving on average, overall moving in the direction in which the electric field is pushing them. So we've got the drift velocity, and now we can relate this drift velocity actually to the current, the number of coulombs per second passing by any point, and we can do it this way. So imagine a segment of wire, got a distance that a length that we'll call d, and just imagine it's a long, thin, this wire is a long, thin cylinder. And the cross-sectional area, right, the area that you'd get if you just made a slice perpendicular to the axis of the wire, we'll just call that area A. And let's think about the current right there. And of course, the current right there is just the amount of charge that passes by that point divided by the length of time it took for that much charge to pass by. Charge over length of time. Now let's imagine that this length of time is long enough for all of the positive charges that started out just sitting here in somewhere in this region, long enough for all of those positive charges that were sitting still, but then when you turn on the electric field, they become part of the current, long enough for all those to empty out. So in particular, this time interval has to be long enough for the positive charges that started out way over here to get all the way to the other side. In other words, those charges are all moving at the drift velocity, of course. So it would take, so the drift velocity, if a particle here moves at the drift velocity and gets to here after delta t seconds, then that means the drift velocity is just that distance divided by delta t. Right, we're imagining that all the charges here that were available to become part of the current have been empty, have been pushed out of that region by by turning on the electric field, and then they feel the forward pushing electric force. So how much charge was in here to start with? Because we're imagining that this much time is the time it takes for all the charge that was just sitting around here to get emptied out. The way we think about it is that that total amount of charge is just involves three factors. This thing here, which is say the charge per particle times the density of available particles. Not every particle, not every atom or molecule in this length will become part of the current. Some fraction will. So there's some number of particles in here that will eventually become part of the current. And we usually think in terms of available particles per unit of volume. Available particles per cubic meter, our normal unit for volume. So this number here is actual density of available particles available to become part of the current when you turn on the electric field. So to get the actual number of particles, you multiply the density times the volume. So here's particles per unit of density per cubic meter. Here's the number of cubic meters. So those two factors gives you the number of particles in there that will become part of the current, and you multiply that by the charge per particle. And now you've got the total amount of charge that's going to flow out of this region and past this point in delta t seconds. But of course, this is the wire is just like a very long, thin cylinder, so its volume is just the length times the area. Length was d, then area. So now, what have we got here? Current is total charge that's moving out of that region. Times the length of time it took to move out. That total charge was just charge per particle, density of available particles, length of the wire times the cross-sectional area or the thickness of the wire, and then divide by delta t. But look at that. Length of the wire times delta t was just the drift velocity. So current in that wire is just charge per particle, density of particles that are available to become part of the current, times drift velocity times area. Usually we're not so much interested in how thick, how thin the wire is. In that case, we want some kind of measure of current that's independent of the thickness of the wire, and we invent a different kind of current symbolized with J. We think of it as a kind of current density, because what it is the coulombs per second current divided by the area through which that current is passing. So if you divide all this by A, here's I and divide it by A, what you end up with is simply charge per particle, density of available particles times drift velocity. So just write these rules here for handy reference. Now it turns out that this J current has a simple relationship with the electric field. Right? You have to have an electric field in order to produce the electric force that pushes all those current particles forward. And the relationship is a very simple relationship between the electric field and the J current, the current density, and it's just like that. The strength of the electric field is just directly proportional to the current density. And this thing here, lowercase Greek letter sigma, is the proportionality constant, and this proportionality constant actually measures how good of a conductor the material is. We call this number the conductivity. Conductivity is just a property of the kind of material that wire is made of. Good conducting material will have bigger values for conductivity. In other words, good conducting material will, for any particular value of electric field applied to that wire, good conductivity means bigger conductivity. That gives you bigger current. That's really a fundamental rule. The fundamental rule of electric current we call Ohm's law. This is actually one version of Ohm's law. It's not the most common version. It's probably not the version that you saw if you took high school physics, but it is a version of Ohm's law. We can do a little bit of work here to turn this into the common version of Ohm's law, and that works like this. Just start with our definition of J. Regular coulombs per second current equals, J is regular coulombs per second current divided by area, and that's equal to conductivity times electric field strength. But remember, electric field strength is closely related to the potential difference. So I can write the electric field strength this way. So now this equation becomes current over the area through which that current passes equals conductivity, size of the potential difference over D, multiply both sides of the equation by A, the area, and then what have I got here? Current equals conductivity A, size of the potential difference over D, which is just the length, the distance between the points that have these two different potential differences, or equivalently, it's the length of the segment of wire, where this is the difference in potential between the two ends of that wire. Let me rewrite that a little bit. Delta V equals distance over A. 1 over area in the denominator is the same as putting area up in the numerator. And let me write a different symbol here, lowercase Greek letter rho, which is just the inverse of the conductivity. This is 1 over equal to 1 over rho. So now I've written 1 over rho instead of writing conductivity. And the name we give to this symbol is resistivity. Just as resistivity is a number that, conductivity is a number that measures how easy it is to make current flow through any kind of material, resistivity is the number that measures how difficult it is to make current flow through any kind of material. We usually combine all these factors into just one thing because these factors all have some effect on how easy or how difficult it is to make current flow. And we lump them into a number that we call resistance, which is just resistivity times the distance between the two ends of the wire. Usually we'll refer to that distance as a length, so it appears like that in the textbook, divided by the area or the thickness of the wire. So if we define a resistance that way, then this whole denominator is just R. And now our equation is just current equals the size of the potential difference over R. This is the common version of Ohm's law that you will have seen if you took high school physics. But it's essentially, it means the same thing as this. This is telling us that you have to have a potential difference in order to get a current. But of course, we know that if there is a potential difference, that causes an electric field. And this tells you that you need that electric field in order to have current. Basically the same thing. It's the potential difference that produces an electric field, and once you have that electric field, charged particles can feel a force that'll push them in the forward direction. That push in the forward direction will match the backwards drag force that they feel, so that as long as that forward push is there, they'll keep moving at a constant velocity. And the constant velocity for all those charged particles gives a current. Let's just look at one. Well, no, let's stop here. That's a lot to think about. We'll don't want to overload you with stuff. We'll deal with this a little bit more in class.